Alright everybody, so we have made it to 14.7, the end of the chapter. And so the thing about this section is that it's really going to kind of bring together some of the different pieces that we've already done. So this is a great way for us to have, a single problem where you have to work multiple different angles and aspects of the stuff we've covered in this chapter to demonstrate your knowledge. So that really kind of moves it up on the list when we think about things that show up in section 2, for instance, of our exams. Alright, so you may have some familiarity with acid-base titrations. We talked about them a little bit in Gen Chem 1. We were talking about strong acids coming together with strong bases. You may have experienced a wet lab where you had to do one of these titrations. And so typically what happens is you either start off with an acid and you add a base, and then you stop when there's some color change, or you do the opposite. You start off with some base in a beaker or an Erlenmeyer flask, you add some acid to it drop by drop. Again, you're going to stop when the color changes, and we're going to call that the end point. Okay, and so what we talk about with titration is we're adding some amount of acid that is going to neutralize a base, or some amount of base that's going to neutralize an acid. So we're trying to put in the appropriate number of molecules for them to cancel each other out, because if you add a proton to an OH hydroxyl group, you're just going to make water, and that is the neutralization effect. But now that we're in Gen Chem 2, we've been talking about equilibrium systems. We've been talking about weak acids and weak bases. So when we're talking about titration now, we're talking about taking a weak acid and adding in some strong base. We're talking about having a weak base and then adding in some strong acid. So now let's look at a visualization of what we would have done in Gen Chem 1, where we had a strong acid. So we're going to have a bunch of strong acid, say 25 milliliters of 0.100 molar hydrochloric acid. We know that's a strong acid. And we're going to add to it some amount of sodium hydroxide. So we're going to add the strong base to our strong acid. So before we add any of that base, we have an acid with some pH that's less than 7, and we haven't started adding any drops of sodium hydroxide into it yet. So at that point, what is the pH of our acid? Well, the pH is over here on our y-axis, and so if we've added 0 amount of our sodium hydroxide on that x-axis, that means we're down here at the 0 point. And then what is the pH? Well, it's just going to be the pH of what that acid is. So that is going to be what is the strength of that acid, and so hydrochloric acid is a really strong acid, so we end up with a pH that's really low. We have complete ionization, so it's going to be related to the concentration of H's that are released in a solution, so it's a matter of also looking at that concentration of HCl. So that's how we end up with our first point on this graph, looking at being very down here in that bottom left corner with a low pH when we haven't added any sodium hydroxide. But we know that the point of a titration is that we're going to slowly add some sodium hydroxide. So what's going to happen as we start to add that sodium hydroxide? Well, now what we're doing is we're putting in OHs. So if we were down here at this first time point where you just have a bunch of H's, all H pluses, and now you start to drop in some sodium hydroxide, what's going to happen? Well, now that sodium hydroxide and that proton are going to get together and make water. So now you have neutralized one of those protons. Now you have decreased the overall number of protons that are in this solution. So what's going to happen is that our pH is going to start to rise. As you add more and more sodium hydroxide, you're going to start to neutralize those protons. Less protons means a higher pH. So that means that just over time, you're going to add more and more sodium hydroxide. You're going to rapidly start to change the pH until you get to this point where you're almost going vertical. And so by the time we have added drop by drop sodium hydroxide to the point that we get up here around 25 milliliters, now what we have done is we have taken 25 milliliters of our HCl at 0.1 molar. We have added to it sodium hydroxide, 25 mils of sodium hydroxide, also at 0.1 molar. And so now we have actually added the same number of H's as we have added the same number of OH's. So at that point, in the titration of a strong acid with a strong base, we end up with an equivalence point right here at pH 7 because they have completely canceled each other out. Now you no longer have any more H pluses that are in solution, and so if you continue to add that sodium hydroxide, now you are adding OH's that are going to not have anything to cancel out with, and you are rapidly going to become more and more basic. And so what we see is this curve which goes up rapidly and then flattens off, because now it's just a matter of more and more of the base being added to that solution, and then the conjugate base of your acid, that Cl minus in this case, is up there affecting the pH as well. Okay, so this is what it looks like in Gen Chem 1 when we did that titration. And so we had chosen phenolphthalein. Phenolphthalein was the indicator that we like to use with those kind of labs in Gen Chem 1 because around pH 8 it is clear. But if you go above pH 8, say you go up, around pH 9, it turns pink. And so we know when you are close to the equivalent point because you start to see this pink color, right? And that equivalent point is here on a very steep linear line right there. And so it doesn't take very much at all of the hydroxides, of that sodium hydroxide, to get into that pH 8 or pH 9 range. Okay? But we say that you've overshot the reaction if you ended up with a highly pink solution, and that's because now you would have ended up, say, over here or over here in your titration. And so now you would have been further away from that equivalence point. And so it would be harder for you to be able to tell us precisely how much H plus was in that solution when you started. So this is what would happen for our general Gen Chem 1 version of strong acid being titrated with a strong base. And of course, a much prettier picture looks like this over here. And so there are different phases to this curve that's, again, drawn much better than I would. And so the initial state that we described was all H pluses, right? That was all because of the acid. So the initial state, it's going to go up or down on this pH scale based on which acid you're using. Hydrochloric acid, pH around 1 when it's just at a 0.1 molar concentration. We saw examples on our chart of a pH of 0 or a pH of -1 if it was a very concentrated acid. So that initial state is going to vary based on the identity of the acid and the concentration of the acid. So then what we have is, of course, our equivalent state. And so with the equivalent state, they've labeled it nicely here, we're going to end up with no more H pluses. This is the point where all the OHs have been added and they have canceled out all of the H's. So that means that we had to have the same number of moles of protons as we had moles of hydroxide. So that means that if there was a region before we reached equivalence, we're going to call that pre-equivalence, and we're going to say there's some H pluses there. And then we have post-equivalence. And in the post-equivalence phase, we still have no H pluses, right? We canceled them out already at the equivalence point. And now what we have are OH minuses. And so now we're moving into the basic or alkaline region of the pH scale. And so it rapidly becomes that basic solution because there are no longer any H's to cancel it out, and there's no buffer present or anything else to really slow it down. So it's that rapid incline. And so what you see is that as we move toward the equivalence point, we do in fact go vertical, right? So it's a very sharp transition when we're trying to decide, is this solution going to be acidic or basic? Well, it depends on a very low number of adding H pluses or a very low number of adding OHs is going to influence the pH tremendously right there at the equivalence point. So in this titration of a strong acid with a strong base, we only need stoichiometry. We only need to know what are the ratios that these acids and bases come together to cancel each other out. Well, HCl has 1 proton. Sodium hydroxide brings 1 hydroxide, so they're going to come together 1 to 1. So we can just use that stoichiometry to figure out the number of moles of one acid required to cancel out with one base. And so that is the simplest version, and that's one of the reasons why we teach it in Gen Chem 1. So now let's move to a little bit more complicated scenario where we're talking about a weak acid being neutralized by a strong base. So now instead of having 25 milliliters of our strong acid, HCl, now we're going to talk about having 25 milliliters of a weak acid, so something like our acetic acid, still leaving it there at that 0.1 molar concentration. We still have the pH on the y-axis. We still have the volume of sodium hydroxide, strong base, on the y-axis. We're still adding that drop by drop. It's still 0.1 molar, so it's still in the same concentration as the acid that we're talking about. But now we need to think about how our graph is going to change. As we add that sodium hydroxide, now what we're doing with a weak acid is setting up a buffer system, because we are now going to have some amount of acetic acid and its conjugate base, acetate. And so both of those are going to be in solution. So we're not going to have the rapid transition where we just immediately go to the equivalence point. Because we're actually setting up a buffer system, we're going to have a narrow window where the pH isn't going to change very much. And so when we first start off, we're going to have some acidic pH, but then what's going to happen is that that amount of OH that we add isn't going to change the concentration that much, again, in a small window where there's some buffer capacity. And so we get this narrow window where we don't see a rapid change. But at the point where we cancel out all of the acid, we're still going to reach that equivalence point. And so now you see that rapid increase again. And then eventually it's going to start to flatten out. And so the equivalence point, again, is going to be in this very tall region. Labeled it blue last time, so it's the equivalence point. But you'll note that that equivalence point is no longer at pH 7. When we have the titration of a weak acid with a strong base, the equivalence point is actually going to be above pH 7. And that, as we'll see later, is because of the hydrolysis of salts. So we're actually going to have conjugate base that's present from the weak acid, and so when that is still in solution, that is going to lead us to have a basic solution. And so that's why it elevates the pH at the equivalence point. So again, with this titration of a weak acid and a weak base, they're still going to cancel each other out, but we just have kind of this strange area, this window down here, which is a buffer range, where we don't really see that big change in pH when you add sodium hydroxide. So again, there's going to be a much prettier picture of this, right? So this is what it would look like in our textbook. We can talk about the phases. The initial state is going to be all acid, and so we can call that all acid. And so again, the pH that we choose to intersect on this y-axis is going to be based on the identity of the acid and also the concentration of the acid. We know that a weak acid like formic acid is going to have a different dissociation constant than, say, the acetic acid that we've also dealt with, right? So that's going to change where it intersects over there, but it's still going to be intersecting on the acid side of the pH scale because we're starting off with an acid. It just happens to be a weak acid. So then they give you this buffer zone, right, where there's this area where we don't actually end up with too much change in pH. So that's pre-equivalence. So our pre-equivalence has this buffer zone, and in the buffer zone we're going to have both the acid and its conjugate base. So even though we started off with just the weak acid, the sodium hydroxide comes in and turns some of that acetic acid into the acetate ion, because the OH from the sodium hydroxide is grabbing the proton off of acetic acid, and all that can be left is going to be that acetate ion. So that happens in the buffer zone. Now there is this sweet spot in the buffer zone, which is an inflection point. And so you see this point where it's kind of arching up, and now all of a sudden it's kind of arching in the opposite direction. So we call that an inflection point, and so that's going to be the midpoint that's described over here. Now there's a special case of what's going on at the midpoint. At the midpoint of the titration of this weak acid, we're going to have equal concentrations of the acid and its conjugate base. And so at that midpoint of the titration, that's where this is actually going to be its absolute best buffer, right? Because a buffer, we said, was going to be equal amounts of the weak acid and its conjugate base, or the weak base and its conjugate acid. So that when they're equal to each other, that is the place where it's the best buffer. And so if you visually inspect this, you see that adding a little bit of acid would move this to the left. Adding a little bit of OH would move it to the right, but it wouldn't move it very much. That's what we talked about with that previous example. You add a little 1 mil of sodium hydroxide, the pH changed from 4.74 to 4.75, right? It was because of this flat region, where it's a little flatter right here, where adding a little bit's not really going to change the pH. That's where it is going to be its best buffer. So that's what's kind of unique about this titration curve, but then afterwards it goes on to have an equivalence point. Again, the equivalence point is going to be where you've added enough sodium hydroxide to cancel out all of the acid. So if we had 25 mils of 0.10 molar acid, then it takes 25 mils of our same concentration of that base, because they are a 1-to-1 ratio, in order for them to cancel out. Now again, we said this equivalence point is not set at the pH of 7, because at this equivalence point you have acetate ion in solution. And as we'll see in a few minutes, when that acetate ion is in solution, it's going to grab some protons off of water, just like we learned about during the hydrolysis of salts lecture. And when it does that, it's going to set up that system to be basic or alkaline. And then of course we would have a post-equivalence phase, and so that post-equivalence point phase is going to be described by an excess of that sodium hydroxide. So now we're just going to have a lot of OH. Alright, and that's why we end up with such an alkaline pH at that point. Alright, so those are the different phases. So it's just easy to see them side by side. I don't know, I like kind of seeing side by side pictures. I don't know if that means anything to you. By looking at them side by side, you can say, great, look, our strong acid is going to have a starting pH that is lower than our weak acid. That's just a function of how much they dissociate in solution. If you want to look at the equivalence points, well, on the strong acid being titrated, equivalence point is going to be at pH 7 when it's with a strong base. Now when we look at the weak acid being titrated with a strong base, look, we've got an equivalence point that has actually been elevated because of the presence of a conjugate base. But they do still have an equivalence point that is at the point where we have the same number of moles of our OH as we have moles of our acid. And so for that, because these are coming together in 1-to-1 stoichiometric ratios in both of the systems, one system where it was NaOH plus HCl, and one in which it was NaOH plus CH3COOH. Again, those come together 1-to-1, right? This one OH is going to come and get this one proton. This one OH is going to come and get this one proton. And so that 1-to-1 ratio and the fact that they have the same concentrations means that we're going to end up with the same mole to mole equivalences happening at 25 milliliters of both. So when we want to calculate these, right, because this is going to be the last slide before we move on to some actual calculations, we want to think about which phase are we in. Are we in the initial phase with no sodium hydroxide being added to our weak base? If so, we just need to think about what our acid is. What is the Ka? Can we use an ice table with an x squared over the initial concentration of our acid minus x? Can we make that 5% approximation? If we make that 5% assumption, then we can move on saying that not a lot of it dissociated, and it makes our calculation much simpler, so we don't have to use the quadratic equation. In the pre-equivalence phase, well, we need to treat this as a neutralization. So we'll have to do like we did in our previous example, where we talk about how many moles do we have, what is the neutralization balanced chemical equation. At the midpoint, if you're able to recognize that at the midpoint you have equal amount of acid and base, then we can talk about the pH equaling the pKa. That is a relationship that exists that would allow us to use the Henderson-Hasselbalch equation instead of having to do an ice table. If you don't recognize it, we'll just solve it by an ice table. At the equivalence point, we have neutralized all of the acid with an equivalent amount of the base. So if you know that's the scenario that you're at, it'll tell you something about how you have to go about it to calculate the pH. If we're calculating the pH of one of these weak acids being titrated with sodium hydroxide, a strong base, then what we're going to need to do is calculate how much of this conjugate base is remaining in order to figure out the pH, right? Because it's going to be above pH 7 because of the hydrolysis of salt, because of the way that counter ion, that anion of the acid, is going to interact with water. And then if we're post-equivalence, we really need to understand what is the excess of the base that we have, because that's going to be the dominant way that we determine what the pH is. We can get a pOH, and then we can convert that into a pH. So we're going to do all of that in the next lecture, and that's because we're going to have pretty much an example of each one of these phases. Calculate the pH at the initial state, at the pre-equivalence, at the equivalence, and at the post-equivalence. And so we'll work through all of those. So you're welcome to go ahead and close this one, and then when you're ready to do some calculations, you can move on to the next one.